Okay, so question 1. So first off, what is a Lewis base? Well, we know that Lewis bases donate electron density. So if they donate electron density, then we need to have some electrons that can do that. And two types of groups that you want to look at are groups that have lone pairs. So lone pairs or pi bonds. And for question 1, we see we have a methyl. And when you draw a methyl, what do you have? You have some hydrogens like this. Do you see around that carbon that there's no lone pair or pi electrons? So that is not a Lewis base. But when you look at the sulfur species right here, you'll see that it has 2 lone pairs. Those can act as a base. Ammonia, NH3, it has a lone pair that can be used as a base. And then MEOH is simply called methanol, and Me is a methyl. So we have a methyl attached to a OH, and the OH has 2 lone pairs. So that can act as a base. So the answer for question 1 would be A. Which is the most acidic? We can see all the answer choices are in terms of pKa, and we have learned that the smallest pKa is going to be the most acidic. And so that one right there, that's 10,000. This one right here is 1,000. 10 to the negative 3 is 0.001, and 10 to the 5 is 10,000. No, let's see. 1, 2, 3, 4. No, actually, that's 100,000. 10 to the 5 is 100,000. So when you look at all those numbers there, what's the smallest one? Answer C. So let's take a look at number 3. Condensed structures. Well, let's just go from left to right. Try to color code this the best we can here. That's a CH3. CH3. And then we have a CH. A CH. And attached to that CH, we are going to have a OH. Right there, OH. And also attached to that CH, we have a CH2. CH2. And to that CH2, we have a second CH2. And is that a CH2? No, that's a CH. So that one doesn't work. So what about answer, if we start over with, let's take a look at answer choice B. CH3, CH3. CH, CH, O, O. We have a CH right there. CH, CH2, CH, CH. And what's attached to that CH? We have a chlorine, and a chlorine, and then a methyl. So the correct answer choice would be B. Which acid is the most acidic? Now remember, these are now Kas, so larger the Ka, is going to be the most acidic. And so we have 10,000 right here for answer choice A, and then 10 to the 5 was 100,000. So though the largest number there would be that one. So the answer choice is D. Question 5, which species is the conjugate acid? When we take a close look at what's happening, that guy is water, and then what does it get converted to? Hydroxide. So that means that this species is what is this species right here doing? It's donating a proton. So that's by definition makes that an acid. But is it a conjugate acid? Nope, it's just the acid. This right here is the base, and that gets converted into the alcohol. And so that would be the conjugate acid. So the conjugate acid would be answer B. Which of the following is the correct zigzag structure? Well, we have a methyl, 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 methyl. So that all works out. We have a CH, a CH, a CH. Nope. That's a CH2, and that's just not right from the beginning. Then we have our OH. OH attached to the CH. Boom. Nope, that is okay. So those are all off the table. Now it's just down to those two. And we have a CH2, CH2, CH2. Another CH2, CH2, CH2. A CH. A CH is there, and then that's just a chlorine. So that's not it. We have a chlorine, and then attached to that would be our methyl, which is that one. So that is our answer choice right there. So how many sp2 hybridized atoms are in the following molecule? We know that we are looking for atoms that have 3 electron groups around them. So 3 electron groups around the atoms. So what we see here is, let's just highlight one of them. So here's a carbon right there. How many electron groups are around it? If we zoom in here, we see that there's going to be 2 hydrogens coming off of that carbon. And when I count electron groups, I see 1, 2, 3 electron groups around that, making that carbon sp2 hybridized. If I take a look at this oxygen atom right here, there's a lone pair. So there's 1, 2, 3 electron groups. So that oxygen atom is sp2 hybridized. Now I've warned you guys and taught you guys that amide nitrogens are always sp2 hybridized. And we're like, well, how can that be? That's 1, 2, 3, 4. There's 2 hydrogens coming off. That's 4 electron groups. But remember that the amide nitrogen has that lone pair that can resonate in. When you look at that resonance structure, when you look at it that way, looks like that. That nitrogen is now positively charged. And if I expand out the hydrogens right here, like that, you can see that there's 1, 2, 3 electron groups around that nitrogen, making it sp2 hybridized. So counting this all up, let's do it in red. How many atoms are sp2 hybridized? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What's the hybrid? So the correct answer is C. But what is the hybridization state of that carbon or that carbon? Both of those are going to be sp hybridized. So question 8, for which of the following molecules do you expect the pKa value of the OH proton to be the most similar to molecule X? Well, that looks the most like that guy right there. Answer A. Which of the following does not represent a pair of resonance structures? So if we look at this, A, if we take those electrons, put them there, those there, and those there, you will get the structure on the right. So that checks out to be a good resonance structure. Molecule B right here. Well, a negative charge on a carbon implies that we have a negative charge there. So could we take those electrons, put them there, and then go like that? Yep, that checks out. C. We have some lone pairs on that oxygen that can resonate in to give us this molecule on the right. So that checks out. And then molecule D, how is that a resonance structure? Well, they're making it abundantly clear that this oxygen atom is number 1, and that oxygen is number 1, and you can see the numbering scheme. And you can see that this is not a resonance structure because atoms have moved. So we see that we have a hydrogen on oxygen 1, and then that hydrogen moves to oxygen 5. So that is not a resonance structure, hence the correct answer. Which carbon has the most S character? Now when we're talking S character, and we look at the electron configuration for a sp3 hybridized carbon, let's say, what does that mean? We have gone from the ground state. The ground state electron configuration would be a 2s and a 2p. Okay, so for carbon, it would look like this, okay? But let's not worry about the electrons. Let's just worry about the configuration. And if we want to go to a sp3 hybridized, then that means we have to take an s and 3p orbitals and hybridize those into 4 degenerate orbitals. And those would be sp3. If I want to turn it into a sp2, then I need 1, 2, 3. And so those 3 that I just circled will be hybridized. And then this one that I did not circle, meaning I did not hybridize, will remain the same. So that's sp2, and there's our p orbital. Now, if I want to have the electron configuration for a sp, that means 1, 2. And then we have the p's right there and the sp. So when we take a look at the hybridization state of the sp, we can see that these hybridized orbitals right here consist of 1p and 1s. So that is, what I circled in blues, where did those orbitals come from? It came from this guy and that guy. So that means that we have 50% coming from a s and 50% coming from a p orbital. And then if we take a look at the sp2, how did we generate the sp2 hybridized orbital? We got that from 1 of those and 2 of those. So what's that? So what's that percentage? That's 1 S and 2 P's. So that is 1/3 of S. So of the 3 total orbitals used, 1 S was used. So that's like a 33%, 33.33333% S character. So those orbitals right there have 33% S character. And then you can see what's going to happen with our sp3. All right, for sp3 we have that one, that one, that one. So we have 1 S and 3 p orbitals. So that's simply 1 out of 4. 1 out of the 4 orbitals that are getting hybridized are coming from the S. So the sp3 hybridized orbitals are 25% S character. So when the question is asking the most S character, we are simply just trying to find the ones that are sp hybridized. In this particular, well, that orbital, hybridized orbital, has the most S character. But if you look at that carbon right there, that's sp3. So we could say, hey, that has 25% S character, 50% S character, and then let's say number 2, that would have 33% S character. So number 9 has the most. So that would be answer B. Okay, in the following equation, what is considered a base? Don't worry about the distinction between base and conjugate base, just identify the species that are acting as bases. So in this generic equation here, what's happening? That grabs the proton. Now you see that we've added the electrons there, which now makes that negatively charged. So that's the mechanism going in the forward direction. So that goes from there to there. And then we have there to there. So what we could do is label it. That's going to be our base. That's our acid. That's our conjugate acid and conjugate base. Now I want to show you the reverse reaction here. Let's take a look at these mechanistically. How does that work? Well, I'm going to take this BH and expand it out a little bit. What's happening? A- is the conjugate base, which now can come, grab that proton. Then the BH bond is going to break and put the electrons there. And then that goes to that. And then that goes to that. So the answer to this question then, what are the bases? That guy and that guy. So this has multiple answers. Okay. So identify and label the acid and the base. So now we're going to do this without having, we're just going to have fictional elements here. So what's happening? We are going from here to there. So we're losing a proton, so that makes that the acid. And then we are going from here to there. And that's gaining, so that would have to make that the base. And so that would be the conjugate acid, and that would be the conjugate base. Like that. At equilibrium, circle the side of the reaction that will be favored. So how do we do that? Well, we find the acids, which we identified up above. And what's the pKa of this fictional molecule? We'll see that it's right there. So that has a pKa of 15. And then the ZH is that guy. So that's the pKa of 25. So equilibrium favors the side where you find the weakest acid, which is right there. So equilibrium is going to favor to the right. By what magnitude? 25 minus 15 equals 10, and that is actually 10 raised to the 10. So it is favored to the right pretty strongly. You see mechanism arrows draw out the mechanism for the reaction going in the forward direction. So we can do that using this. Let's clean this up a little bit. Mechanistically, how's that going to work? Well, we'll take those lone pairs, grab that proton, break the X hydrogen bond, sticking the electrons on the X, and there it is. Question 13, is this a valid resonance structure? No, it is not. Why is it not? Because you're violating rules. How many hydrogens are coming off of that guy, and that guy, and that guy? So the amount of hydrogens have to remain the same on all of this. So if that did happen, that would have to be a positive charge right there. And then when you take a closer look at that carbon, you see that you've generated a Texas carbon right there. There's 5 bonds. Let's make sure we can count those bonds so you can really see that it's 5 bonds and a Texas carbon. 1, 2, 3, 4, 5. Okay, dry resonance structure. There's many answers to this problem. We have to realize that there's a lone pair. So we could draw a resonance structure like this. So you would have your 6-membered ring like that. Positive charge on that carbon. That's one resonance structure. You could then take that resonance structure that you just made and see those pi electrons could come like that. And then you would have double bond there now. The O is still negatively charged. Now where did that positive charge go now? Well, if we keep track of the protons, right there still has to be protons there. How many groups are around this carbon right there? 1, 2, 3. So that carbon does not have an octet, so that has to be positively charged. And that's one of the resonance structures. Okay, so let's look at this one. Is that a valid resonance structure right there? No, it is not. Because you've broken so many rules, or 2 major rules. The first one, you cannot take pi electrons and skip the adjacent bond and go to the next one. That can't happen. Okay, and the reason why that can't happen, you could explain using orbitals. In order for pi electrons to move around, they have to travel through p orbitals. And this is a sp. This carbon is sp2, and that's sp2. And what do sp2 hybridized carbons have? They have p orbitals that are unhybridized. And so those electrons in that double bond can travel through those p orbitals. But when we look at this carbon right there, that is a sp3, and that has no p orbitals. Another thing that you would see and say, hey, this can't do that, is because you have 2 hydrogens coming off of there. So now you have also generated a Texas carbon right there. Okay, rate the following resonance structures from most significant to least. So what's the first rule about resonance structures? Do the atoms have an octet? That oxygen has an octet, so does that one. This one has 3 lone pairs, that has an octet, that has an octet, but this carbocation right there does not. It only has 6 electrons around it. And then this one right here, that oxygen has an octet, and so does that oxygen. That has an octet. So based off of the first rule, we can say that this guy is the least significant because it has an atom that does not have an octet, and the other two do have octets. Rule number 2 states the structure with the least amount of formal charges will be the major contributor. So this one on the left has 0 formal charges, this one has 2. So that makes that guy the most significant out of the bunch. So if we numbered these, 1, 2, 3, the most significant would be 1, then 3, and then 2. Draw these 2 resonance structures for this molecule. In order to do this, you need to understand what has lone pairs, like that. So we could draw a resonance structure where we are going to move those pi electrons to the oxygen atom. So we could draw it like that. H, I didn't move that lone pair. I have the O minus plus like this. So that's one resonance structure that we could have drawn. Another one that we could do, we could take that lone pair and go in between, because what do we see? We have a lone pair adjacent to a carbocation. So that's a feature that we can recognize. O minus, so that will now have to be positively charged. And then we have this. Okay. Let's see, we could then, let's go this way. We could take those pi electrons, move it there, and then those back to the nitrogen. That's a plausible structure. Go there, like that. And if I did that, where would the positive charge be now? Right there. And then could we draw another resonance structure? We have a carbocation adjacent to some lone pairs. So those could come down. Double bond, O minus. And that would be positively charged like that. Okay, so that's doing it stepwise. But what if I wanted to go from this first one right here? Well, let's just go from the original all the way to there. Is there a way that we could draw the arrows to do that? Going between those two structures. Okay, so let's make sure I'm abundantly clear here. We're starting with this molecule, and if I ask you to start from there and showing with your mechanistic arrows or your resonance arrows, how do you go from this structure to that structure? Could you show the flow of electrons on how that happens? Well, we see that we have a double bond there, and there's single there. We also see that there's a double bond there, but now it's single there. We also see double bond there, single bond there. But let's pay attention, we have a lone pair right there and a lone pair there. So that, the lone pair there and the lone pair here did not move. So we just have to keep track of that and move the electrons that are moving. And so we could do it like this. We could say we'll take those, move them in between the, let's zoom in a little bit, shall we? We could take that lone pair and go in between. Those go there, and then those go like that. So you could do it you could use 3 arrows to go and draw resonance structures if you like. You could do it stepwise or all in just one swoop. Both are valid. Question 15, identify aldehydes, ketones, carboxylic acids, amides, and acid anhydrides. So this, just got to get out your flashcards and memorize these functional groups here. So there's our aldehyde, there's an amine, there's an alcohol, there's a ketone, there's an ether, there's a carboxylic acid, there's an amide, there's a acid anhydride. Okay. Identify and label the primary, secondary, and tertiary alcohols. So this one right here, that is an alcohol, but what kind? Well, we look at the carbon that's directly attached to the oxygen and then count how many carbons are directly attached to that red dot. 1, 2. So that makes that a secondary alcohol. Here's another alcohol right there. We look at the carbon that's directly attached to the oxygen. How many carbons are directly attached to that red dot? 1, 2, 3. So that makes that a tertiary alcohol. And that guy would be a primary alcohol. That is not an alcohol. That is the carboxylic acid. Identify and label the amines. Okay, now that's a little bit different. We have an amine, and all we have to do is ask how many carbons are directly attached to the nitrogen. 1. That's a primary amine. This one right here is a secondary amine. This one is a tertiary amine. And then this one right here is a quaternary amine. And then it said also to find a primary carbon, a secondary carbon, and all that good jazz. So let's see what we can find here. So this right there is a primary carbon because it's only that carbon in blue is only attached to another carbon that's directly attached. So that's a primary carbon. So a secondary carbon, let's find a secondary carbon. There's a secondary carbon because it's attached to that guy and that guy directly. So that's a secondary. What about, let's clean this up a little bit. What about this carbon right there? 1, 2, 3. So that's a tertiary carbon. Do we have a quaternary carbon in this molecule? Let's see. That guy right there, because there's 1, 2, 3, 4 carbons directly attached. So there's our quaternary carbon. Okay. Question 16. Okay, so for the first one right here, we know that the smaller the pKa value, stronger the acid. But what is it asking? For the weaker acid. So that guy's the stronger acid, hence that will be the weaker. Another pKa comparison, 3 is smaller than 8, so that makes this guy the stronger acid, hence that the weaker. Now we're using some numbers here, and we know larger the Ka, stronger the acid. So we're comparing 100 to 1,000. 1,000 is larger than 100, so that's the stronger acid, and so making that the weaker. Now we have a comparison of Ka to pKa. So now we have to look at this a little bit differently, okay? And so how I like to do this is, what does pKa equal? pKa equals the negative log of our Ka. Okay? So if I take the pKa and do the negative log of the Ka, what's the Ka? 10 to the 7. 10 to the 7. Okay? So what's that going to give us? So the negative log, or let's just take a look at the math like this. What's the log of 10 to the 7? That's going to equal 7. But we have this negative sign right there. Okay? And so that's going to be a negative 7. So when we go the pKa of negative log of 10 to the 7, that equals negative 7. So we rewrite it, pKa equals negative 7. That equals that. So those two terms right there are the same. So we could take this whole problem now and rewrite it. We could say, hey, I don't want to look at this as a Ka. Let's just look at it as a pKa. And we just discovered that the pKa of that equals negative 7. So now we can see that that and that are exactly the same. So those are the same. Now, if we take a look at the last problem right there, we could do the same analysis. pKa equals the negative log of 1,000. If we take the log of 1,000, that equals 3. Okay? And so we can scratch that out, but remember, there's this negative sign here. Okay, so we have the Ka of 1,000 also is the pKa, which equals negative 3. So now we are comparing the pKa of negative 3 to the pKa of 3. And this is a smaller pKa, which makes that the stronger acid. Hence, this guy over here is the weaker. And since we're asking for what's the weaker acid, there it is. Okay, let's clean this up here. Okay, labeled acid, base, conjugate base, indicate which side will be favored. So in this particular problem, you just need to remember your pKa's. Where's your acid here? That's an alcohol, about 16, carboxylic acid. Let's make the math easier for us here. We'll just say 15, and carboxylic acid is 5. Where's the weaker acid? To the left. How far to the left is it going to be favored? 15 minus 5 equals 10. That's 10 raised to the 10. So it's favored to the left by a factor of 10 to the 10. It also asks us to find, this would be our base, our acid, conjugate acid, conjugate base. Do the mathematical calculation. We already did that, so we answered that question. Okay. So I think that addresses that issue right there. Okay, as always, if you need any help, reach out.